So I'm Laszlo. I'm in the Funston group at the Monash node. And I'll be speaking today about quasi-periodic light. So the basic question we want to answer here is, what kind of order can be found in the universe? And I'll narrow that down a little bit to order in the light in the universe. So there's several different kinds of order that might be very familiar. One of which would be symmetry. So some familiar symmetries would be translational symmetry, like in this image, or you can have reflection symmetry, or rotation symmetry. You can also even have systems that have all of those symmetries. But there are other kinds of order which are not symmetries. So quasi-periodicity would be an example of that. And if you take a look at the video, you can see here an example of a quasi-periodic object. That's just to illustrate the concept. Quasi-periodicity does not have symmetry, so it doesn't have translational repetition, and it doesn't have rotational repetition. And if you reflect it, it doesn't look the same. But it does have some special directions, and it does have long-range order. So a simple mathematical example of quasi-periodic order is if you take a wave and make some copies of that, and then you rotate the copies to be separated by equal angles in 2 dimensions. So if you had just one wave, that's just got translational periodicity. It's periodic in one direction. If you've got 2 waves and they're at right angles, then it's periodic in 2 dimensions. But if you have 3 waves or more, then it is quasi-periodic. So quasi-periodicity is something that has been found in the claddings of interesting pieces of architecture since ancient times. It was popularized as a concept by Roger Penrose in the form of Penrose tiling. And sometime after that, Daniel Shechtman discovered quasi-periodic crystals using diffraction. Since that time, those quasi-periodic crystals had also been found in nature, as well as many, many kinds of synthesis. And they continue to appear in architecture. So in the Salesforce Transit Center in San Francisco, there's a really nice cladding that's got a quasi-periodic pattern cut into it. So point I'm getting at here is quasi-periodic matter, or quasi-crystals, are well established. We're looking at the structure of light, and can light have quasi-periodic structure, as well as matter? So our approach to this is to use a light-emitting diode. The light-emitting diode was fabricated with molecular beam epitaxy. So it's a gallium nitride, and then there's several thin layers of indium gallium nitride quantum wells on top of that, and another layer of gallium nitride above that. So we flow current through the light-emitting diode, and the electrons and holes meet up in the indium gallium nitride layers where they form excitons, and those excitons recombine to make light. The light-emitting diode was then processed with electron beam lithography to make a whole bunch of holes in it. And the holes give it the quasi-crystalline structure. And then the holes were filled with quantum dots just by spin coating them in. So this is a scanning electron image of the inverse photonic quasicrystal. So I'm calling it inverse because it's made of holes instead of being made of particles. This kind of image is scanning an electron beam across the surface and measuring the scattered electrons. And I'm mentioning that because there's going to be a lot of different imaging techniques in this talk, and I wanted to really make clear which ones are which. In order to investigate the matter, like in the previous slide, instead of investigating the matter like the previous slide, we want to investigate the light. So to do that, we use near-field microscopy. Near-field microscopy is a type of atomic force microscopy. So some of you might have seen that in your lab, but it's an optical technique. So what it does is it uses a feeler that scans across the surface of the sample and it can measure the shape, but it also measures light. The way it measures light is by acting as a waveguide. So it's a pipe for light, and it's very, very sharp. And at the end of that pipe, there's an aperture that lets the light in. The resolution of the optical image is based on the size of the aperture and not on the properties of light. So this allows us to get superior resolution to other imaging techniques, down to about 50 nanometers. We also get the shape of the sample at the same time, the topography. So any of you who are doing nanofabrication might be interested in this technique if you're fabricating something that has interesting optical properties. We also have the ability to measure in 3 dimensions. And unlike conventional microscopy, you don't get everything scrambled by the interference of light, because you look inside the interference pattern. All right. So this is an example image of near-field microscopy of the light-emitting diode. This is the blue light that comes from the light-emitting diode, ignoring the oranger light that comes from the quantum dots that are embedded in it. And we do find that there's a quasi-periodic pattern in this. This is an image of the emission from the quantum dots that are occupying the holes in the photonic quasicrystal. So it's a longer wavelength channel. And we find that the peaks are in totally different places for the quantum dots, but they continue to have this quasi-periodic structure in the light. This is a cathodoluminescence image. This is a really different kind of imaging mode. So the near-field microscopy sees where the light's coming out. The cathodoluminescence sends in a beam of electrons and then detects light from everywhere. So what we're measuring here is what's the position where when you inject an electron, you get a photon out. So this is sort of more like, where does the energy come from rather than where does it get converted into light? So one thing we notice here is we can see the quasi-periodic structure of the quantum wells. And we see these really nice rings. The rings are caused by 2 things. One is that the holes that make up the quasicrystal are trapping the electrons when they come in. So if you've ever used an SEM, you might have used a Faraday cup, which captures electrons. That's essentially what's happening here. And then also inside those holes, the surface of the quantum well is exposed. So the electron doesn't have to penetrate through any material in order to excite the quantum well. Something we don't see here is we don't see any kind of resonant modes, which is something that has been frequently reported in the literature as a property of photonic crystals. And we think the reason for that is probably that those resonant modes are actually further into the infrared than the light emission of this particular photonic crystal. We also don't see any cathodoluminescence of the quantum dots. So we think they're getting quenched somehow. Anybody happens to have an idea for how to see that, that would be very interesting too. So to really understand structure, it's often very helpful to look at things in reciprocal space instead of real space. Reciprocal space is also known as Fourier transform space. All it does is it takes position and it replaces the position with the repetition frequency. So that's frequency in inverse position dimensions. All right, so in this graph, we're using wave number, which is units of per micron. So the average of the whole image is in the center, and then things that are periodic in different directions form a ring around that. So for quasi-periodic structure, you expect to see some spots, and you expect those spots to have rotational symmetry. And the rotational symmetry should be higher than 6, or it could be 5. So if it's got 4-fold symmetry, that's a regular crystal. If it's got 6-fold symmetry, that's a regular crystal. 5, 7, or higher is something different. For our device, we're expecting 12-fold symmetry, and this is just an illustration of what you'd expect to get. This is the reciprocal space structure measured with Laue diffraction. If you've done Laue diffraction before, what we did is actually totally different. So this is just achieved by shining a laser onto the photonic crystal. And we have to use a long wavelength compared to normal Laue diffraction because we're accessing rather large length scale structure. And we do in fact find from the laser scattering that there's a 12-fold symmetric diffraction pattern, which indicates that it is quasi-periodic. There's also some other features in the center, which are properties of the substrate. This is the SEM image. So again, this is looking at the matter. The SEM image has, when presented in reciprocal space by Fourier transforming, has 12-fold symmetric pattern. So again, in real space, it's not symmetric. But if you look in reciprocal space, there's this very obvious symmetry. Cathodoluminescence imaging, again, that's scanning the electron beam across the surface and measuring the photons coming out. Again, we have the 12-fold pattern. We get some extra peaks that are instrumentation effects, and then we have some substrate effects as well, which are not terribly important. So for the near field microscopy, so this is directly measuring the structure of the light itself. Again, we have the 12-fold peaks and some substrate effects in the center as well that, again, aren't so important. So in conclusion, near field microscopy is a technique that has superior spatial resolution. It can go down to 50 nanometers under certain circumstances. And the reason it does that, does have that superior resolution, is that the aperture, which is the hole the light has to go through, is placed in contact with the sample or very close to it. And the size of that hole determines the resolution. Whereas conventional microscopy has a hole that's far away, where your microscope objective is, or your telescope is, and that limits the resolution. Okay, so it also enables us to measure the light field in 3 dimensions. That can let us give us shape information, and that can give us information about the light above the surface, which I haven't included in this talk. Quasi-periodic light is ordered, but it's not periodically ordered. It's a fundamentally distinct category of order. And you can recognize that by representing your data in reciprocal space. So in this talk, we've demonstrated quasi-periodic light with near-field microscopy. Thank you. I don't think so.
Any questions in the room? Sean?
Quick question. So I can see that it's ordered. You have 12 pieces before. How does that order actually look like in a large scale? So you have the thing there. But when I see, I guess I'm thinking about order differently. I see no, I don't see it.
All right, so how do you tell that it's ordered and you don't see a pattern? And okay, so one answer to that is use reciprocal space, and if you see peaks that aren't at the center, then you know it's ordered. But if you want an eyeball approach, you take your structure and you look at it on edge, and if you rotate it, you'll see some lines that go a long way. And you can pass this around later to try that. Whereas if you look at it face on, you can't tell. If you look at it on the edge, there's some obvious patterns.
Great, thank you.
Oh yeah, so it's related to the concept of a moire pattern, but it's not exactly the same concept. Yeah.
Hi. So at the beginning of the talk, when you were talking about quasi systems having order at long range, I'm just curious what is classified as long range in the scenario, or is it system of?
All right, what does long range mean? And I think that the answer to that is opinion based. Yes. If the range is long enough that your diffraction pattern or Fourier transform has peaks, then I think it's long range. So liquids and glasses are usually considered to be disordered because in ordinary diffraction experiments, they don't have those peaks. They have some short range order, but they don't have long range order for that reason. Interestingly, if you do things just right, some liquids do have peaks. I learned that recently, but only under very certain special circumstances. So there's always a gray area. So in our case, we have about 10 micron large scale order. The proven. And then for people who do crystals as opposed to optics, I think that they're usually microcrystalline. But I don't know. There's some pictures on the internet of macroscopic quasicrystals that have facets that can't be explained by ordinary crystals. So like they're like, I think they're dodecahedral facets or something like that. So, you know, for crystals, it is possible to get pretty huge amount of order long range.
Great. Was there a question from Jihan?
All right, so under the best conditions, 50 nanometers spatial resolution optically is the highest you can get with the commercially available tips. That's the highest specified by the manufacturer. There's some random variation in the quality of the tips too. So if you get lucky, it might be a little bit better. But
I think there's a question from Nicolau in the chat. Could you just read out that one?
all right, question from Nicolau. So if you have two patterns overlapped, there are regions that cannot match. Could this be exploited somehow for interesting physics? Okay, so I think that's what we were trying to do. So I think that the interesting physics here is showing that we have got light that has that property. So you know, it doesn't repeat, it doesn't have translational order, but it does have regions that are similar. Now, the next part was for an optical cavity, which contains two quasi-periodic lattices on either end. That's interesting. I have no idea what would happen if you did it in a cavity.
Great. Thanks, Laszlo.
Thank you.
Thank you.